Hello everyone. We are going to see the today's topic, that is method of minimizing spherical aberration in the lenses. We are knowing the spherical aberration. If you want to see, you can see my video in which it is clearly explained. To remove this type of defect in the image found by the lenses, we have several processes through which it is minimized. In that, the first process is by using stop. How we are doing to remove the parallax image? How can we do the removal of spherical aberration by this? So this diagram very carefully here. Here in this diagram, let us consider a convex lens. Here in convex lens, consider parallel ray of light. This is the principal axis. Light passes along principal axis undeviated through the lens L1. This ray is called paraxial rays. We are allowed to fall paraxial rays, and this paraxial rays condense at a focal point called FP. This is the marginal ray. Marginal rays are away from the principal axis, and here in it, these are stopped by certain obstacle. So by stopping marginal rays, the image can be obtained at a point. In place of this enlarged image is formed, the blurred image, this fainter image is formed in. There is one more way through which, suppose this is A process. In process number B, we are stopping paraxial rays. In this paraxial rays, here is a lens. L2. Here in this, the paraxial rays with this principal line is stopped by obstacle, is not allowed to fall over the lens. Only marginal rays are allowed to fall on it. This marginal rays condensate, converting, meeting at a common point. This point is focus of marginal rays FM. So here in both the diagram, in diagram number 1, we are stopping marginal rays, allowed to pass only paraxial rays, meeting at one point. In the second, we are stopping, not allowing to move the paraxial rays, rays, only marginal rays are allowed to move. So meet at one point. So we can remove the spherical aberration by using this technique. Second method is by using plano convex lens in a specific manner. See, we are going to use a plano convex lens and see by which spherical aberration can be removed. So here in C, first of all, consider plano convex lens. In this plano convex lens, we are going to take first of all paraxial rays. See the paraxial rays here, refracted from first surface here and finally condenses here. This is at a point of FP. Second rays away from the principal axis called marginal rays. This marginal ray is represented by double arrow, refraction and meet at a focal point here. See, in this case, this is known as focal point for marginal rays. This is abbreviated length of the image. Image is formed from here to here because intermediate rays meet between FM and FP. So abbreviation is this. One thing is a common. Here refraction takes place 2 times. First from this convex surface, thereafter from the plane surface too. Now see in the second diagram first of all, then we will compare the both diagram here. See, this is a principal axis for the plano convex lens. Now this time the same lens is used in a different way. The plane surface first of all, thereafter the curved surface. But in the first case, the curved surface was first and plane surface was later. So see here in this case, paraxial ridge near to the principal axis, refracted here through the only the second surface, not through the first surface. Why? Because it is perpendicularly fall on the plane surface. So single refraction, refraction is obtained. Thereafter this paraxial rays meet at a focal point of FP. See what happened with marginal rays. Same like as the paraxial rays, marginal rays is also allowed to fall on plano convex lens. First on plane surface, passes without refraction. Thereafter refraction takes place from a second side. So these rays meet at a point of marginal focal point, and it is paraxial rays is here. So image is formed between these 2 points. See, in the second process, aberration is more than, let this aberration is of D2, and in first case when image is formed is a D1, in this image D2. Here in this D2, aberration D2 is greater than D1. What this is? If plano convex lens is used due to first way, the curved surface towards the object, in that condition aberration can be minimized. One line one may say that deviation produced by the lens is a minimum. In which case it is a minimum? See, when it is shared by the two surfaces equally, here like the first case. So this is the second way through which the spherical aberration can be minimized. Now we are going to see the third process. Now the third is by the use of crossed lenses. This is purely theoretical idea. See the theory. What is the theoretical idea? This theoretical idea for minimum spherical aberrations. According to this theoretical idea for spherical aberration, paraxial rays, we know paraxial rays. What is the paraxial rays? Which is near to the principal axis, satisfy the condition. What is the condition to satisfy? If R1 by R2 follow the formula refractive index n in bracket 2n minus 1 minus 4 by n 2n plus 1. So for this, see a crossed lens, concept of the crossed lens here. Let it is line of principal axis, and here in this consider a lens. See in the lens. So before making a lens, first of all see, if we take a glass having refractive index 1.5, normally we know the refractive index of either flint glass or crown glass lies around 1.5. So keeping this value in the formula above, R1 by R2 is equal to, this is 1.5, 1.5 3 is 2, 1.5 3 is when you 1.5 into 2 is 3, minus 1 minus 4 by 1.5, 3 plus 1. It becomes, on solving, 1 may get minus 1 by 6. So ratio of radius of curvature of a lens is minus 1 by 3, 1 by 6. If it satisfies the condition, then you see a concept of this type of a lens. Let a convex lens is made by cutting these two, combining this here concave lens. This concave lens, see very carefully, the radii of curvature of first R1 and second surface, this is R2. This is by concave lens. If radii of curvature of first here R1 is negative, R2 is positive here in this case. Clear? And here in this case, if we are keeping the value of R1 and R2 is 6 times C in the diagram, the ratio of R1 by R2 is satisfying 1 by 6. Then for minimum spherical aberration, the paraxial rays, see the paraxial rays here near to the principal axis. This paraxial rays suffers 2 time refraction, first from first concave surface, then after second concave surface. In that, scattering in different directions seems to come out from a single focal point. So aberrations is removed by this process. Now see the fourth process through which the spherical aberration can be minimized. This process is by using two plano-convex lens. We use two plano-convex lens separated by finite distance. So see hold the procedure through which by taking two plano-convex lens, when we place an optical bench up to a certain distance, see how spherical aberration is minimized. So for that, see first of all, this green line represents the principal axis. Consider two plano-convex lens, L1 and L2 here in the use, like the diagram. Their curved surface are towards the side of the object. Both the lenses are separated by finite distance. Let's see this optical center of both is O1 and O2, and this O1 and O2 is separated by a distance D here. Let how the ray diagram, let a parallel ray of light, let a object is here P at this place. So parallel ray of light parallel to the principal axis allowed to fall here on the plano-convex lens. If plano-convex lens is not here, it will go in this direction, but because of this plano-convex lens, let it refracted in this direction, and angle of deviation, let it is denoted by delta. Further, when this refracted ray falls on the second plano-convex lens L2, again phenomena of refraction takes place. And final image, let it formed at point capital G here. If second lens is not in the existence, then this refracted ray must follow this path here. So naturally this ray will fall the focal point of the first lens, let it is f1, and distance from here it is given focal length of convex lens L1 here in the diagram. So final image is formed at D. The deviation again take place due to the lens L2. Both lenses are here made of same type of material. It is important that the second lens is placed before the focal point of the first lens. This is the main important point is here. Let the name of points are here given. Let this point is A. This is a point B. Now let O1, O2, A, B, C, F1, these are the points. Now see very carefully here in the diagram. Let this point is K. So PK and this line, principal axis, both are parallel line, intersect by line AF1. In that condition, the alternate angles are equal. See, angle A is equal to angle F, equal. Now see in triangle BGF1. This triangle in which two angles are equal. Which two angles are equal? Angle B equal to angle F1 equal to deviation angle. So it means that this triangle is isosceles triangle in which two sides are equal. If two angles are equal, their two sides are also equal. This implies that BG is equal to GF1. See the condition number 1 in this diagram. These two are equal due to both two angles are same. In that condition, see very carefully. See the straight line this is. If this deviation angle is very less, if angle of deviation is very less, in that condition we are doing one very unique idea. What is this unique idea? In which, see in the diagram, if this angle is very small, then BG we are taking equal to approximately GO2, second optical center for. So what we are taking in this condition, VG is nearly equal to O2G. See in the diagram, if you are taking these two equal, then in O2F1, G is a midpoint. So this implies that G is at midpoint of O2F1 here in it. Now see in the diagram very carefully. The image formed by first of the lens at point F1 play as a object for lens L2. So image formed by lens L1 at f1 play as object for length L2. So see this, at this condition, if f1 is the image formed by length L1 is play as an object. So for length L2, see in the diagram very carefully, it behave as a U and it is as a V in the diagram. So write the U is O2 F1 and V is O2G. See in this diagram. Now we are going to use, see this is equation number 2. Now we are going to take length formula. What is this? 1 upon F2 for second length, 1 upon V minus 1 by U. Now see very carefully here in the diagram. U1, see this is F1 and this is a D. So U can be written as F1 minus D. F1 minus D here. See here. We have written this F1D. Again see here in the diagram. This is just half of the total. So V can be taken as F1D by 2. F1D total by 2. So now keeping the both things here in the value, 1 by F2 can be written as 1 by V. It is 2 by F1 minus D minus this is 1 by U and U is 1 by F1 minus D. See in both, it can be written as 1 by F1 minus D. This implies that F2 is equal to F1 minus D. Again it is implies that D is equal to F1 minus F2. See here, if the condition, see very carefully, if the both lenses separated in such a way that D, that is the distance between two lenses, equal to the difference of their focal length, set in this way. If this satisfies the condition, then final image is formed at a single point G. With help of this, the spherical aberration can brought up to the 0 position. So spherical aberration rations can be removed completely by applying this condition by two plano-convex lens of focal length f1 f2 separated by a certain distance in which follow the criteria f1 minus f2. So first focal length has higher focal length than the focal length of a second. So this is for the topic, the method through which spherical aberration can be minimized. Thank you and have a nice day.